we keep track of is how many objects of one or the other type are smashed together to give how many copies of what other types of objects. And the question that I want to address today a little bit is to what extent does one of these levels of description and the constraints that we naturally have in the natural semantics of this level of description influence or constrain what we can do at a more abstract level. So the question is things like does compositional rules of compositional formulas, namely that you can't lose individual atom types and copies of atoms in any one of these reactions. Does this constrain or does this impose some constraints that we can actually identify at the level of these very abstract reactions? And similarly, if we think of actual molecules, does that have any constraints on what kind of reactions are feasible in an abstract sense at this level of, say, compositional formulas? And this is a question that is relevant also very much in practice, because as chemists, and I'm actually, even though it doesn't show very much, I'm a chemist by training originally. In chemistry, you have very different levels of descriptions, starting from quantum mechanics or potential energy surfaces to spatially embedded molecules that you basically think of as more or less classical objects, to abstract formulas where you can think of reactions just as rewriting rules. And this then gives rise to various different notions with their own rules, from potential energy surfaces to concepts like reaction coordinates to systems level descriptions such as very large directed hypergraphs that describe chemical reaction networks. And what we want to know is kind of what are the constraints that one level imposes on the others, or what are the kind of consistency conditions that we need in order to have systems, say, at this very abstract level that we can then also interpret as something chemical. On this slide, this is just represented again, sort of in the other way. We will mostly be interested with these very abstract stoichiometric formulas. We will ask what do some formulas have to do with these, and then of course you could go into all sorts of more realistic questions on, well, how is that actually in real chemistry? Can you actually implement any of these networks in real chemistry, for instance? So if we think of chemical reactions not as individual reactions as I had on the first slide, but at a more systems level as systems of different chemical reactions, then essentially we can think of this whole system as a directed hypergraph, where I use this kind of Koenig representation where the directed hypergraph is written as a multipartite, as a bipartite graph with multiple edges, where the idea is essentially every reaction is represented by a reaction node, which is all these squares that are shown here, and all the compounds, all the vertices of our hypergraph are shown by these ellipses, and every one of these ellipses is actually labeled by the compound that it represents, here drawn as these chemical structure formulas. And we will come back to the question very soon on what kind of questions you can ask on these kind of reaction networks at different levels. So in the first case, we will just think of these molecules as simple labels. They are just more complicated than calling them ABC, but we don't care what their internal structure is. but we actually might care depending on the description that we want to use. So summarizing that again, we have a level of transformation. We have a level where which is a completely formal way of moving around stuff, which we can think of as a variant of Petri nets if we want. We have a level where we actually take part of these or even more of these labels at the individual molecules seriously, and then we can even further start to ask what of these are these reactions in any way meaningful that we describe. Can we also think of them in terms of chemistry? And I will very much be interested in exploring these transitions between levels here. So from a computer science point of view, you can also be interested in these chemical reaction networks as a model of computation, where you can actually look at that in two different ways. You can think of one chemical reaction network endowed with variables that is just a count of how many copies of each one of these molecules we have, and computation then is performing reactions in such a way that at the end we compute certain vectors, certain numbers on certain molecules that we designate, so certain copy numbers at certain molecules that we designate as output. This is actually a viable model, abstract model of computation that has been studied quite a bit over the last 10 years. This is not quite computationally universal, but there is, with very small additions, you can actually make this equivalent to a Turing machine. There is also another way, and that is the generation of different molecules, which in the sense of graph rewriting, which one can also show that this is kind of a viable, interesting model of computation in general. I won't go into that, but that provides a motivation for asking which chemical reaction networks that I can write down formally actually have a chance of being implemented in chemistry. Because if anybody ever succeeds in using chemical reaction networks to actually do some computations in practice, then designing the reaction network in such a way that it performs a particular computation is exactly what programming means in this context. And then obviously it is interesting to know whether all or only some subset of reaction networks that I can dream up could actually even in principle be implemented with real molecules. So very briefly, at the level of molecules, if we go down to this, or we drill down to this question of can we represent chemical reactions in terms of molecules, then every reaction essentially becomes a game of moving around atoms and bonds, and at a reasonable abstraction level, actually at the abstraction level that we use for writing down chemical reactions in chemistry, you can think of that as a game of rearranging graphs, and then we can actually write down certain types of reactions as transformations of these graphs. And these types of transformations again actually then deserve an explanation in terms of actually moving around electrons which form these bonds, which is essentially the kind of explanation that you want in chemistry for saying what is actually a reaction mechanism, what is actually the type of reaction that is going on here. We've played for a long time with actually implementing and working with these graph transformation systems, so with models of chemistry where we only allow a very particular types of transformations between graphs. This is also a topic that's interesting for some point down the road, but I think I should not go into this issue here. So the way you think of that is you basically have a starting molecule and a bunch of rules, and you can build up a chemical reaction network. However, here I want to start with chemical reaction networks at the top level, at the most abstract level, where we kind of strip out all the chemistry and we just write reaction networks in terms of these formal algebraic transformations that basically just say a bunch of possibly copies of different objects can be rearranged to give other multi-sets of objects. This is really what we write here. Every reaction in our system is one of these transformation rules, and one can write these reaction systems in terms of a so-called stoichiometric matrix, which is simply just the coefficients. So for the first reactions, which we write as the columns in this matrix, we just ask what are the molecules, or what are the entities that are consumed in that reaction, and what are the entities that are produced, and that gives us this kind of matrix that just encodes in matrix form what we've written down here as the chemical network. And at this level, we can ask things. If I know what my 5 carbons are and what my 6 carbons are, I can then ask in this chemical reaction network, which is just basically given as such a matrix, is there a way of transforming 6 copies of a 5 sugar into 5 copies of a 6 sugar, or vice versa? So in this case, I ask for fructose as input, which is here, and where is my output? Here is my output reaction. Can I get 6 copies of glucose? And in this case, I get a particular integer flow, or actually integer hyperflow, in this network, in this reaction network, as a solution. So this is the kind of stuff that you can ask in these networks, so or at the level of this stoichiometric matrix. So, or the metabolic flux analysis, optimization of metabolism for the production of certain substances in biotechnology and things like this. This is essentially all done at this abstract level, and you don't really need to look into the details of the underlying molecules. It's really just about flows in these networks. If we want to dive a little bit further into these, then we can essentially ask, so we are given now one of these hypergraphs with some input and some output, and what you would actually want to know is if you get a flow solution, so if we get a connection of some set of inputs to some set of outputs, is this actually something that is also chemically feasible? So can you actually really transform this input into that output in this chemical reaction network, or is there something missing? And the point that there is something missing is that at the beginning, when you kind of start your reaction, you only have your prescribed input molecules, so your input flows and your output flows, but you cannot sort of get any one of these intermediates. So in order to get what I receive from a flow calculation on this network, in order to think of that as a pathway, we also have to find a temporal ordering that tells me that everything that I need in one reaction has already been imported from the outside, or has been produced in an earlier reaction. Otherwise, that particular reaction cannot fire. And there is no way you can make this transformation work in your network, even though the linear convex algebra calculation tells you there is a nice flow that goes from here to there. In order to answer that, and this is very much Cecil's work, the idea is to remodel this integer hyperflow as a Petri net, and then one can check whether the Petri net actually is realizable in the sense that you do the usual checks for empty markings at the end in Petri nets. And that basically gives you a feasible causal ordering of the reactions, while before you only had a set of reactions that have to be present in certain multiplicities in your flow solution. So if you don't get a flow solution, then there is also no way that you can get a mechanistic a stepwise solution, but the existence of a flow solution does not necessarily imply that this is in fact a feasible pathway in the sense that you can make this causally work. The basic idea is essentially to represent the number of available molecules, so the input and the output at the places of these networks. So we basically just add a bunch of marks to the original input, and then we will move these tokens, we will move these marks through the network as the reactions fire. And the rule is that every reaction can only fire if there is the sufficient number of input tokens available for a reaction. So you have to satisfy all the input conditions. Here 2 marks in P1 and at least 1 mark in P2, otherwise this reaction will not take place. So the way how you read this is you need 2 tokens on P1 and 1 token at P2, and then the reaction can fire, and then the output of this thing is 2 tokens that will be shifted to P3. So we still don't have any mass conservation or anything here. We just move these tokens along. So one time firing this reaction T1 takes you from the state on the left to the state on the right. So this one can, in order to do this in a formal way, what one essentially can do is add additional input and output places into the structure of the original network, and then one can play this network through. So Cecil used this network tool Lola to actually compute these causal orders, and one can use these also to represent the kind of stepwise computation of the products from the educts along a certain reaction pathway. So I'm just giving you here a couple of examples. So there's interesting and not necessarily completely intuitive cases where you have flows that are not realizable, so you cannot go through this reaction if you have only 1 input node. But if you just multiply the whole thing by 2, then it becomes realizable. So it may be that you have to have a certain minimum number of initial conditions necessary to make a flow realizable. But this is also not something that you can always do if there is if the reaction needs a catalyst that is not there, that it has not been produced in an earlier reaction, for instance. Then this cannot be realized without kind of borrowing this additional component, this additional compound that you need to start the reaction, which then the reaction will eventually reproduce several steps later, like in this network here, this just happens in the next reaction. But if you don't have a C in the beginning, then the first reaction cannot fire, and then you will not get the output B. However, if you get to borrow one copy of C, then you can run the reaction, and eventually it will recreate somewhere downstream this borrowed reactant C. Again, this is surprisingly difficult to find out whether this can so that this is always possible. Oops, this we already had. So what one can look at is then, does it always work to scale up a flow to make it realizable? This is kind of what one would kind of think from classical flow calculation, from flow computations, where we kind of, so that we can see some of these effects, we always insist that one has to have integer solutions. But if you just want feasibility of the flow, you can simply also do this in over the rational numbers, and then you just get your flow solutions. But it turns out that there is actually networks, and it's not so difficult to construct them, so that upscaling the source, so upscaling the flow, really actually never make the system realizable, and one can give a relatively simple condition under which the flow is not scale realizable, and this basically goes like this. If we have our network and H, which is our hypergraph of this in this network, and we just start with some start sets, or this should be a subset here, then we define the reachable set from S as everything that in the following form. First of all, the start set is reachable, and then if whatever is produced, whatever is the left-hand side of a reaction, so the educt side of a reaction, if that is in the reachable set, then also the right-hand side of the reaction, so the products have to be added in the reaction, and you kind of just iterate that. That gives you a notion of reachability in the hypergraph, and we can ask what is its edge set and what is its vertex set, and then essentially we only have to ask if all these vertex set V that has non-zero flow. So if all the edges that have flow in it consist only of vertices that are reachable, then scale realizability may hold. If there is vertices in the edges that we need in the flow solution that are not in the reachable set from the start, then we know that this network is never scale realizable, and we have to borrow additional types of molecules from somewhere. So this is an interesting question, because it basically distinguishes between the pure linear algebra solution and a causal solution, and basically tells us that not all the solutions in for flow-through networks, so for production pathways in networks that we get from the algebraic picture, is actually also causally feasible. Let's just jump over this stuff here. So this summarizes this part a little bit. So pathways that we can define as flows is one thing, but not all these pathways or flows can actually be realized in terms of reactions actually firing. So all the logical conditions for a reaction to run being satisfied. There is notions of weaker notions of realizability by scaling up the flows or by borrowing additional molecules, and this is apparently kind of an important a part of understanding what it means to have kind of a distributed type of catalysis. So this notion of network catalysis seems to be related to these realizability questions. Cecil's paper on this stuff was published at the ISPRA, so that came out a few months ago or so. So now I want to switch to the main topic of what I wanted to talk about, and this is this question: are there constraints on the networks that preclude things from being reasonable chemistry? And there is a little bit of a modeling freedom that I want to build into this whole thing, and sort of without going into the letter soup on this slide. Essentially, there is the notion that every chemical reaction is in principle or kind of logically reversible. But that in general doesn't mean that it actually that you actually can make it run into both direction without sort of putting in an infeasible amount of energy. So we may want in our reaction system all reactions or a subset of reactions to be operationally irreversible, in the sense that we only if the equilibrium constant under standard conditions is much smaller than 1 or much larger than 1, then effectively we get irreversible reactions where only the edukts or only the products dominate once we come reasonably close to equilibrium. And in this case, reasonably close essentially means a little bit of time after we started the reaction. So we can model chemical reaction systems and just assume everything is irreversible. We can also want to model chemical reaction systems where we basically define for a subset of reactions that they are they're effectively irreversible. And this makes it a slight difference in the results in the following. So
excuse me, Peter. Sorry to interrupt you really quick. So I don't know if this was clear, but we have 2 speakers and it was half an hour and half an hour. And I noticed on your slides you're exactly at the halfway point now. So by any chance, did you intend this to be a 1-hour talk, or?
I can stop earlier. So how long am I supposed to be talking?
Minus 3 minutes at this point, I think.
Okay. So then I think yeah.
But please, like, we would like you to. I mean, yeah. This next part, I think all of us are very excited. So I hope that's okay with Jeremy. Like, just start a few minutes.
It's perfectly okay. I can even postpone my talk if you want, so that we can let.
I'm very sorry. I kind of completely overlooked these. So let me just gloss over this stuff here and essentially go. So the only thing I just skip all the complicated stuff here and essentially just do 2-3 more slides and then I stop. Okay.
Perhaps. I mean, this is all very interesting. Perhaps the organizers can allow for another slot at a later occasion.
Yeah, I agree.
It would be a pity to rush. I mean, maybe we have a teaser now. And
yeah, so
but
this is kind of what I'm thinking. So so if we think of this network in this at this completely abstract level, what you can see is that you can have combinations of reactions that all look completely reasonable if you just write them down formally, but what they do is they compose two reactions where obviously you violate in this case conservation of mass or conservation of particles, because there is a linear combination, positive linear combination in your system that allows you to do a net reaction that says A plus B plus C gives A plus B plus C plus something else. And this is not possible because we now happily generated this X out of nothing in our system. And the logic of this is basically, okay, so this may all be fair and good if we do this in open system, but if we write down a chemical reaction network, then that chemical reaction network has also behaved reasonably if we close it off and pack it into a closed system where it cannot exchange mass, it can just get rid of energy to the outside or whatever. But no mass exchange, and it still has to behave reasonably. So this thing here that's written up here cannot be a legal chemical reaction network. And the same thing that you can do is you can also do this same stuff essentially with the question of energy. So whenever you have a cycle of only forward reactions, then that will generate that will generate energy out of nothing, and that also should not happen. And where I will stop is essentially to say what we have essentially is a theorem that says where is my take-home message? One. So no, this is not the one that I wanted. Oops, where is this thing? Okay, yeah, so this is what I wanted. So a reaction network is consistent with mass and energy only if and only if it's reversible completion, which basically means I just add all the reversible reactions that logically should exist. Then I cannot make combinations of reactions that generate or destroy mass from nothing, and so this is the same thing as the already Horn and Feinberg, and so already found that this network have to be conservative, but now we also know the other direction. This is not only necessary, this is also sufficient. And the second condition is if we allow irreversible reactions, there cannot be irreversible futile cycles, so irreversible cycles that have no net production and no net consumption. And this is sort of a baseline for everything that behaves like a chemical reaction network that we need to have. And with that, I stop. I'm sorry for having overlooked that I should have shut up already 5 minutes ago.
Yeah. So